Welcome back to Arxflix. Today, we're diving into a fascinating new paper titled Idempotent Generative Networks. This research introduces a novel approach to generative modeling, focusing on training a neural network to be idempotent. An idempotent operator is one that, when applied multiple times, produces the same result as the first application. Think of it like a "make it real" button for images. This figure illustrates the core idea of idempotent generative networks, IGen. Real images, denoted by X, are invariant to the model F, meaning f x equals x. The model is trained to project other inputs, like noise Z, onto the manifold of real images by optimizing for f z equals f z. Traditional generative models like GANs, VEs, and diffusion models often require specific input types, like noise or conditioned images. What if we wanted a single model that could take any input, even corrupted or modified data, and project it onto the manifold of real images in one step? IGN aims to be this global projector. It's trained to map a source distribution, like Gaussian noise, to a target distribution, like realistic images. IGN achieves this through three key objectives. 1. Reconstruction. Real images should be mapped to themselves by the model. 2. Idempotence. The model should be idempotent, meaning f z equals f z for any input z. 3. Tightness. The manifold of images that are mapped to themselves should be as small as possible. This figure highlights the importance of the tightness objective. Directly optimizing for idempotence can lead to the manifold expanding, which is undesirable. IGN addresses this by introducing a separate term that encourages the manifold to tighten around the real data. IGN offers several advantages over existing generative models. 1. Single-step generation. IGN produces outputs in a single step, similar to GANs, but also allows for sequential refinements, like diffusion models. 2. Consistent latent space. IGN maintains a consistent latent space, making it easier to manipulate and interpolate images. 3. Generalization beyond training data. IGN can effectively project corrupted or modified data back onto the manifold of real images. 4. Simplified editing. IGN can accept both latent variables and real-world instances as input, eliminating the need for inversion steps. The paper demonstrates IGN's capabilities on MNSD and Saliba datasets. This figure shows examples of generated images from IGN. Notice that applying IGN multiple times can correct for artifacts and improve the image quality. This figure showcases IGN's ability to project images from different distributions, like noisy images, grayscale images, and sketches, onto the manifold of real images. The authors acknowledge that IGN's performance is not yet competitive with state-of-the-art models. They plan to scale up IGN by training larger models on more data to realize its full potential. This research represents a promising new direction in generative modeling, offering a unified approach for projecting any input onto a target distribution. Stay tuned for future developments in this exciting field. Thanks for watching Arxflix. Don't forget to like, subscribe, and share this video with your fellow researchers. See you in the next one. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.